Well, good afternoon. Let me get organized a little bit here. You can see by the title of my talk, it's a good follow from what Simon had to say, and also it's a good following from where you're located. If you walked more than 5 minutes outside this building, you walked within the center of the study area that Simon presented and I will present on in the central portion of Hong Kong. Well, as a background, urban air quality has been studied quite a bit all over the world. But urban exposure has not been studied as much, and the factors related to urban exposure have just barely been scratched in the past. There have been studies, especially in Europe, Southern Europe, some of the Asian cities, including Jakarta, and some cities in India, to look at how densely packed people, bad traffic, and poor air quality intermix. And what I'm going to talk about today, I'm going to use a bit of an example from a study that was done at City University a couple years ago, right here. I'm going to kind of try to stay away from science and go more towards things you might want to know about policy, or at least the implications of science. I have to talk a little science because that's what I do, but I'll try not to do too much of it. And the objective of the study, the base study that I'm going to be talking from, was to in fact evaluate the impact of traffic volume, the composition and nature of that traffic on air quality, and especially on street side potential exposure situations. And I'll go through briefly experimental work, the setup for it. I'll talk about the findings. I'll talk about the implications of our findings, and then bring you up to speed on what we're doing to extend the work into new areas to answer more questions. Well, Hong Kong, as Simon suggested, is a fairly special kind of a Asian city. It's very compact, where we have air quality, people, transportation, urban design all working together to basically pose quite a human health risk, and also a real challenge to air quality planning and urban planning people and technologies. We've kind of got in many respects, the things that make Hong Kong so special also make it a difficult problem in terms of air quality and urban design. And so I don't forget, and Simon mentioned this as well, is one of the things in all of these pictures is you're going to see a lot of people. We walk everywhere. Sometimes I walk an hour a day, but we always walk to some sort of transportation, to some sort of a location. None of us either can afford a car or can afford a parking place for a car, so we don't drive. California, where I'm from, I have 3 cars and I drive everywhere, but here it's not a good thing. And this slide is an interesting kind of summary of what the challenge here is. Again, as Simon mentioned, we have a very unusual urban geography. We have a very high density, and we have a high density of tall buildings. To stuff all the people into the buildings, you have to go up. You put the roads close together and the buildings close together, and people go up. So on the left-hand chart, you'll see what looks like just a bunch of needles sticking up out of the ground, and that's the density, the geographic density of the population in Hong Kong. And on the right-hand picture, you'll see the same kind of a demonstration of the urban density of a city we think of as being dense, London. Well, London has nothing in terms of urban density compared to some of the some of the Southern European and Southern Asian cities. That sort of a chart tells us other things as well. You could almost, as you saw in Simon's down-looking picture from a quadcopter, those spikes could just, instead of being urban density, they could just be the buildings themselves, if you want to look at it that way. Makes it very hard for urban air monitoring, urban air modeling, and urban air planners who want to deal with air quality to actually make a guess at what the air quality, even in the street next to where they're making their measurements, is, because there might be a 40-story building between them and the next block. So quickly, I'll go through the experimental design of what we did related to this study and to this area. We made measurements for about a week, including weekdays and weekends, with repeated measurements of on-road air quality and on pedestrian level air quality related to exposure. We quickly found out what we thought were weekends in Hong Kong are not weekends in Hong Kong. Weekend in Hong Kong is Sunday. Weekend is not Saturday and Sunday, it's Sunday. The traffic activity and business activity usually spans Saturday here. The pollutants we measured, again, as you heard earlier, are some of the common pollutants related to traffic exposure, traffic emissions, ultrafine particles, which are very small particles, black carbon, especially from diesel engines, NO2 from various kinds of combustion, PM 2.5 because there's lots of concern in the urban environment about PM 2.5. But actually, and I hope to remember to point this out to you, vehicles and most combustion sources are not a large source of PM 2.5. PM 2.5 is largely formed in the atmosphere from other components. Black carbon and other things do contribute to the mass of PM 2.5, but PM 2.5 is not really a good marker of exhaust. We also, at the same time, with the help of people from Civic Exchange, we made measurements of actually visual observations and counts of vehicle activity during these periods at several locations in the central area. We counted by type of vehicle so that we could determine whether it was light-duty diesel, heavy-duty diesel, buses, cars, motorcycles, so that we could characterize the sources or try to characterize likely sources of what we were able to see in terms of air quality. We picked 3 major roadways near here. One, and I'll show you on a map where they are, but one of them is the roadway right out here. I'll just show you instead, but they're, these are the 3 roads, you might say. And I'll see if I can get you guys are on this side, and the best map is on that side. Let's see if I can get a shot of him. So this is the roadway. I don't know how that's going to work. Let's put it this way. There's 3 roadways, and you'll see each one of them. This is the kind of road. It's closest to the ocean, or the bay, I mean. DeVoe Road is here. We're going to call it DVRC. And Queens Road is next farther inland. They're parallel roads. Not without much distance between them. I suppose it's certainly less than a kilometer between here and here. 500 meters, just 500 meters separate the roads, I'd say. Oh, I'll go back one if I'm lucky. And just to give you an idea of what we were doing, not tell you exactly how, a little bit about the approach. We were making measurements on the roadside by having an instrumented suitcase with some of our students and staff walking the roadways. At the same time, we were driving a heavily instrumented car on these same roadways, making traffic counts by type. So we made the counts at different locations along each roadway. These are the roads that we walked the most, but all the rest of them we drove repeated routes on to make measurements. All of the measurements are highly time resolved. All of them are using pretty much state-of-the-art sorts of air monitoring equipment. You saw a picture like this. I'll show it twice just so that I can make my point. The three kinds of roads we were doing our monitoring on had some similarities about them. They all have traffic, and they're all tall roadways for urban canyons, as we like to call them sometimes. But there's some differences apparent in this picture, and we'll talk about what these differences mean in terms of interpreting our data. But look at this one first. You'll see that there you can see blue sky, and you can see a lot of blue sky on one side, on the bay side. You look at these two other roadways, you don't see much blue sky, you just see walls. And you also see that this road is lighter, everything around there has got more light coming down into it. These roadways are pretty dark down in the bottom of the canyons. So just remember what the pictures look like. This is the one that's going to be the most different. Here's an indication of the kind of data we were collecting and the density of the data we were collecting. This happens to be NO2 being measured, NO2 being an exhaust gas pollutant, being measured on the roadways by our instrumented van. And this is 2 or 3 hours worth of data assembled with data being collected about every 10 seconds as we are driving along the roadway. You can see the dots resolving. Those are the individual observations for NO2 as we are on the roadways. Now, GPS doesn't always work when you're in these canyons, but you can get an idea where we were. We didn't get lost and get off the roadway. We connected this line. What you can see, this color scale tells you about the intensity, the amount of NO2 that we were encountering on the roadways. And the site right along the ocean, or the bay, I keep saying ocean, are the cleanest. But just maybe 150 meters away on DeVoe Road, we're seeing really high levels of NO2. We'll talk about more about that later. But this area, as you saw on the slide earlier, with a little less detail, this is the area where traffic is really a problem in terms of emissions. We have high NO2 levels, we have high PM black carbon levels, just as you saw in the earlier slide. But we're trying to understand more about why we see those sorts of high concentrations. But why don't we see them farther back here? These are relatively cleaner areas. I'll try to explain that. I just want to show you the kind of detail that we were collecting while we were on the roadways. So for starting to tell the story, we did counts on numbers of vehicles, and we find that the highest count of vehicles is on the roadway nearest the bay. But we find so this is counts, but these other roads don't have that high counts. But as we go in one notch on DeVoe Road, we find that the counts aren't as high, but the concentrations, again, are high for ultrafine particle numbers. For PM 2.5, there's more generally a high area inland. For black carbon, which is related to diesel exhaust, is higher as you come inland in this same area. So this area here, one roadway back in, has the highest of the combustion-related pollutants. But the traffic counts are way higher on this first road. I'm going to try not to talk too much about data. I'll just talk about patterns if I can. I can answer questions later about data if you're interested. But the patterns I want to point out are, first, these bar charts. These bars are the amount, another way of showing the amount of traffic on the roadways. So these are the three roads. Traffic levels are high, and these are by type of vehicle. And as we go to the more inland roads, we find that the traffic counts are much lower. So high traffic counts right along the bayfront. Much lower traffic counts as we go to the two other roadways that are more inland. Again, just separated by 100 or 200 meters of distance. And what we find is that while the traffic counts are low here, the pollutant levels in this case, because I'll look down at my chart and make sure I don't do this one wrong, the NO2 and black carbon levels peak, and they peak. This shows what you're seeing, what you saw on the map. The high levels just inland, one road. They're peaking here. But it's not because of a higher number of traffic. Traffic was higher here. Counts were higher here. Concentration was higher here for these two exhaust-related pollutants of black carbon and NO2. If we take just these the very most bottom bit of information, which is the heavy-duty bus, or we call franchise bus traffic, it was highest, and then we blow that part up. We find that the bus traffic was high here, but the concentrations of those pollutants was low. Bus traffic was low here, but the pollutant levels were high. I won't talk more about that, I don't think. There's differences between weekdays and weekends. This is weekday pollutant information about NO2. Along the bayfront, the NO2 levels are pretty high. Probably because the vehicles are at higher speed and because there are different kinds of vehicles there that are contributing in addition to the diesel buses. And I'm not going to do that one. If we go on a Sunday and look at the same area, that was a weekday. If we go on a Sunday, which I thought was a weekend, it's just Sunday, you find that on Sundays the traffic patterns change and the contribution of pollutants from different kinds of vehicles change because the mixture of vehicles change. In this case, in the morning, The levels on Sunday were much lower in the morning. In the afternoon on a Sunday, the contributions from light-duty vehicles suddenly pops up because the buses are not as concentrated during that period. So that was a very quick run through of the kinds of pollution data we collected, but if our concern is about what people are being exposed to, this is a little more pertinent. It's not totally different, but it's certainly pertinent. So remember, we had people walking with a suitcase on part of this roadway while we were making the on-road measurements. And they did this for many, many different hours on this period. So if we take, again, the roadway that was the most heavily polluted in terms of black carbon and NO2 from buses, and we look at the data that was collected by the walkers on this same general roadway. This is this roadway here. We find that in the very beginning, where the on-road concentrations were the highest, this green mark, is here. That's also where the pedestrians saw the highest concentrations too, the green bar. A little farther down the road, they found intermediate levels, and when they got to this end, the levels were lower. So the pedestrians were seeing the contribution of the on-road emissions that we saw earlier from the pedestrians were seeing the effects of the on-road emissions. They were seeing other things too. One of the things they were seeing was that particles were being formed, ultrafine particles, which are ones that we're very concerned about for health effects, seem to be being formed on the roadways. And the reason we think they're being formed, that's our question still at this point, is that other pollutants were lower at the roadway than they were on the road, at the roadside edge, than they were on the road. Ultrafine particles were actually higher at the roadside edge where the pedestrian monitoring was going on. There are scientific reasons why these ultrafine particles may be forming from the complex atmosphere from the vehicles. And that's actually kind of a bad thing, because together with the directly emitted black carbon and the ultrafine particles, we're getting quite a strong signal from probably diesel exhaust. And as a last little piece from the diesel exhaust question, diesel exhaust is listed by the World Health Organization and by several other international organizations as being a known human carcinogen. So the fact that we're seeing high levels of these and we're able to find them due to traffic exposures is not surprising, but it's a strong signal here in Hong Kong. The vehicles are producing the material, and something about the urban area is causing this stuff to accumulate in the urban environment. So what are the factors that are explaining our findings? Well, one of the things is that the number of vehicles is not the only indicator. Clearly, bus number and activity is important, but it's not the total number of vehicles that count. The origin of the PM-related pollutants is most clearly focused on diesel exhaust and buses. NOx is more complex because we have LPG buses, light-duty buses, and taxis here. What other factors are there? Well, there's urban geography, the layout of the streets, the wind speed and the wind direction, the day of the week, time of day, and the number of bus stops along the way that we made measurements. So these are things we need to learn more about in terms of our projects here. I wanted to show you this one last picture of the kind of findings we have back to why we saw them. Remember, this Bayside roadway could see the sky. It was the area with the most traffic, but because it had better mixing, we think, the concentrations were lower. These two areas had a higher, this one had the highest concentration of bus traffic, and again, very steep walls of an urban canyon. Almost no place to walk along them. It's such a narrow roadway. These are kind of roads you see in other places too. I remember doing work in Barcelona and in Milan. Have very narrow roads with fairly tall and restricted roads that parallel the waterways that affect the wind circulation. They also get high levels of black carbon and NOx. And I gave the way that's basically said that the dispersion situations help capture the pollutants back here. The dispersion is, in other words, mixing. He mentioned mixing earlier. The mixing is related to wind speed, and the wind speed is highest along the bayfront, and it's lowest back here where the concentrations were also higher. So a combination of poor conditions in terms of wind, tall buildings along the roadway, and bad traffic situations make this roadway a really bad place to be. It also happens to be one of the busiest pedestrian areas in the city. In summary, traffic counts don't explain everything. For these two areas, buses, vans, and trucks seem to be the most correlated with the pollutant concentrations we saw. In the CRC region, we saw different traffic patterns. We saw different levels related to urban geography and this open air of dispersion. In terms of what the planners can do with the kinds of information we had, cutting diesel traffic and rerouting buses would be very effective in terms of reducing what a pedestrian is going to be exposed to on these roadways. So we want to encourage walking in the cities like this or in other parts of the world. We have to find a way to keep it in our urban planning situation to take into account meteorological factors, traffic patterns, and where people want to spend their time. And not make for the worst of those, but make for the best of those. For an example from here, you'd have people walk one block over and they'd be exposed to far less air pollution. Or you'd take the buses and goods trucks off of the other roadways and have people walk them. What are we doing in terms of initiatives to learn more about air quality, traffic, and traffic-related pollutants? Well, we're developing more advanced pollution sensors so that we can do, instead of spending hundreds of thousand US dollars putting an air monitoring station in to answer a question about one location in Hong Kong, we're starting to work with sensor technologies that allow us to put an NO2 monitor and PM sizing monitors into a box like this that has GPS, has telemetry built into it, and can give you real-time data wherever you go. If you go to work, you can carry it. Go to school, you can send it with your kids. You have an office, you can get collecting data. So we're taking what traditionally is unaffordable and putting into a package where people can ask questions about traffic or urban or port-related facilities, and making high-quality data possible from a smart box. And this is really an application of Internet of Things technology. The other thing we're doing, which is a direct link to this and our previous studies, is putting about 20 sets of monitors, of complete monitors, into the bus system here. And as Simon has had one monitor running in the, making two pollutant measurements in on the tram system, we'll have 20 buses instrumented for about a year running in Hong Kong, collecting data on roads all over the city and doing telemetry and checking like the quality of the data. We think our kinds of information can inform traffic and urban planning. Without the data, you